Hi guys, we're discussing chapter number 18, DC circuits. This chapter is split into these parts. Just do take note for the combined signs and the set phi's, you stop over here. Alright, the last two portions are only for the pure science students, pure physics students. Alright, before we begin, it's good for us to get reminded of all the circuit symbols because we will start seeing a lot of them again in DC circuits. So I'll just run through all of them very quickly again. So for the pure physics students, there will be another two that you have to remember. I'll introduce them when we reach the portion of 18.4 on potential divider circuits. Alright, so this one is a switch. When it's only like this, you know this is called a cell or one battery. Alright, when it's a collection of cells, we call them battery usually. Alright, this is a DC power supply. Alright, with a curvy wave in the center, it's called an AC power supply. This one you should know, this is a bulb. This one is a normal fixed resistor. Over here, this one is called a variable resistor. You have experienced or used this in lab before. The one that with the line running through the center is called the fuse, practical electricity. Alright, circle with an A in the center is a tool to measure current. This is ammeter. This is voltmeter. This is the earth connection. And finally, this G, or sometimes it's drawn just as an arrow lah. So this one is just like an ammeter, but it's a more sensitive one. We call this a galvanometer. Right, galvanometer, that's how it's spelled. Alright, so let's go straight into the meat of the chapter. The first portion we'll be covering is the series circuit. So what is the difference between a series circuit and a parallel circuit? So a series circuit is one where the current only has one path for it to travel. Alright, so for example, if I look at this, the current is only restricted to go along this path. There's no other path or loop for it to travel. While in a parallel circuit, the current can go here. Once it reaches a junction here, you can either choose to take the red path or can choose to take the blue path. So in this case, there are two possible paths for it to travel. Alright, this is a parallel circuit. Alright, of course it's not only restricted to two. I can have three bulbs together and have it be a three or more path or three or more components in parallel. Alright, so just take note of this. In series circuit, the components are connected one after another in one continuous single loop. There is only one path for the electrical current to flow. In this kind of situation, this is a series circuit. Alright, so let's talk about current in the series circuit. In a series circuit, there's only one path for it to travel. I just need you to remember a few things from current of electricity, which is current is the flow of charge per second. Current, the unit is ampere. Alright. Also sometimes based on the definition, it can be described as how much coulomb of charge passes by a point in 1 second. Alright, in a series circuit, because there's only one possible path for it to travel, if 10 amperes pass by this point here, 10 amperes, also known as 10 coulombs per second, that means I got 10 coulombs worth of charges passing by per second. Over on this side, I should also have 10 amperes. It's not possible for me to have 10 amperes here and then 5 amperes here. If it is, then that means I'm leaking 5 coulombs of charge per second somewhere, which is not possible. So in a series circuit, the current is the same throughout the whole circuit. Alright, so just take note of this. Compared to the earlier example where I only have one resistor, when I have two resistors of the same type inside, then all the ammeters in the series circuit will still give the same current reading. However, compared to the first one where I only had one resistor, these current readings are now half. Now, why is it half, the current? Because if you look at it, the circuit now has two resistors, which means the resistance of the circuit is double, which means it's harder for the current to travel because there's more resistance in the circuit. Because of its harder journey, we can say that the charge then moves slower. So I would expect if just now with only one was 10 ampere, then actually now will be 5 ampere throughout the circuit when I double up the resistance. Alright, so let's look at this. Is the current flowing through the two resistors the same? This is a series circuit, so the current is the same throughout. So the answer is yes. What happens to the current if I remove one of the resistors but then still have a connection wire? Then I would expect that the current would double. So exactly how I know it doubles is because V equals to IR. My resistance dropped by 2 times. My V doesn't change because it's supplied by the battery. Therefore, I expect the current will increase 2 times. So that's why it's double. So in general, what will happen if I add another resistor in series here, or rather if I one of the resistors here, this one, I replace it with a resistance that is 2 times the original resistance. Alright, in general, because whenever I increase the resistance of the circuit, I expect the journey to be harder, therefore the current will move slower. The number of charges that pass by per second will move slower. Alright, in terms of description in the formula, V equals to IR, because the voltage remains the same, my resistance increase, I expect that the current will then also decrease. That's why the current will decrease. Alright, in a series circuit, let's talk about potential difference. I need you to recall first what a potential difference is from current of electricity. Recall that potential difference is the energy each charge has. So sometimes an alternative unit you can use is how much joules of energy each coulomb of charge has. Alright, so if I look at it in a normal circuit, it may look very complicated. But if it looks very complicated, can I ask that you just ignore all the voltmeters? Any meters don't actually play a part in the circuit. So you just focus on the parts that are without the meters. So it's basically just this loop here. Now, in a potential difference situation, or when we're talking about potential difference, when we say the battery is a 3-volt battery, we say what it means essentially is that it gives 3 joules of energy to each coulomb of charge, which means as long as the charge has passed by the battery, it will be given 3 volts or 3 joules of energy for each coulomb. Now, as it travels along the path, as long as it doesn't meet any resistor, then it will still have the same amount of energy, 3 joules per coulomb or 3 volts. Over here, it still has 3 volts. Alright, the other rule that you need to remember is that at the end of the journey, before it hits the battery, it must have expended all the energy. So over here, it must have 0 volts. Alright, if they are the same resistor, and this is a 3-volt battery, then actually the amount of over here 3. Alright, before it expand again, sorry, I go back. Before it pass by any resistor, it is still at 3 volts. Alright, if I look at it, then I need to question how much energy does it have here. If they are the exact same resistor, same resistance, then the charge that is over here that has 3 joules of energy will recognize that it needs to split the energy it has equally between the two, which means it will spend 1.5 here joules and 1.5 joules per coulomb here, which means 3 volts it spend 1.5. Over here it only has 1.5 joules of energy left, after which it will expand the rest, then it will land up with 0. So how a voltmeter works is that I always put the voltmeter wherever I want to measure, one before and one after the component. So let's say I want to measure the potential difference across R1, I put one before R1, one after R1. So what the voltmeter does is that basically you can think of it as a guy here, then he just measures how much energy you have. Then there's another guy at the end after the resistor. What he does is he measures how much energy you have. So he sees at the start you have 3 volts. After pass by the resistor you got 1.5, which means he can make the deduction that you have expended 1.5 volts of energy across the resistor. The same for this voltmeter also. Before it goes past this resistor, I see that I put one before here, there's a dude here, and he will measure, oh, this fella has 1.5 volts. Then after the resistor, it has 0 volts. So he recognizes that 1.5 joules per coulomb of energy is wasted here, or 1.5 volts. Alright, so what is then interesting is what you notice is that these two add together must always be equals to this one. You can somewhat think of the battery as the input, how much energy is given, and the potential difference across all the electrical component resistors is how it spends the energy that it got over here. So all in all, the energy it had at the start must be equal to how much is expended throughout its whole journey. So that's why we say the potential difference in a series circuit is the sum. Alright, so this is the summary for series circuit. The current is the same throughout the whole circuit, but the potential difference is the across the whole circuit is the sum of all the individual potential difference across each component, like so. Alright, so the very final point that we have to talk about, because we talk about V, we talk about I, of course we need to talk about R lah. So how do I find the effective resistance or the total resistance when I have two resistors that are in parallel with in series with one another? So if I were to look at this circuit, you would know that the journey will be much harder for the charge. Alright, you can think of it about the tunnel analogy that I covered in class using when I was covering the R equals to rho L over A, the resistivity formula. So each charge, if there's only one resistor, it knows that, okay, this is how much I have to expend. This is my challenge for the whole journey. But when I have placed another resistor in parallel, you basically extend their agony, because you make it that they have to go through the tunnel 2 times lah. So that's why when we talk about effective resistance, it is the sum of the individual resistances. Alright, so this is it. Resistance in a series circuit is the sum of all individual resistances. I'm going to leave this here and zoom in for a while. You can pause whenever you need, but I find it easier when I can write things like this lah. So when I have a normal circuit with I don't know how many resistors lah, as many resistors as you want lah. Alright, the current in a series circuit is the same. Now I know this is not familiar to you, main branch or total, it doesn't really make sense. Alright, the current that is coming up from the battery or going into the battery, we sometimes use main branch or total. Because the current is the same, then I1, I2, I3, I4, I5, how many resistors you have will all be the same. So in series circuit, the current is the same throughout the whole circuit. But in a series circuit, the potential difference or the total voltage here, or the EMF of the battery, must be equals to the sum of all the energies or all the individual potential difference across each component. Alright, and finally the total resistance, sometimes we also call it the effective resistance, is the sum of all the individual component resistance. This one you must remember. You have space in your notes, please copy this down. Alright, the next portion we're talking about is parallel circuits. So for parallel circuits, again, it is a circuit through which you have two or more components placed in such a way that it allows for two or more paths for the current. So for the charge coming out from the battery, it walks here, then suddenly it reaches a junction. Then you can either choose to take the red path or the blue path. If I add one more light bulb, then I can have a third path. So as long as I have more than one path to travel, we call them parallel circuits. Alright, the current in the parallel circuit is the sum of all the readings on all individual components, all individual branches of the current. So let's talk about this. If the current coming out from the battery and reaching this main branch here before it splits is 10 amperes. Before it hits the junction again, it's still at 10 amperes, because 10 coulombs of charge are passing by per second. Over here also should have 10 coulomb of charges passing by a second. But then once it reaches the junction and split, if over here I have 5 amperes of charge or 5 coulomb of charge passing by per second, it means that over here I should also have another 5 coulombs. That means the sum of all these two branches must equal to the amount of charges passing by here per second. You can think of charges as literally physical people walking around here lah. If I got 10 people passing by here per second, and then I got 5 people here, that means over here I must have had the other 5 walking here lah. Alright, then after that, once they recombine at the junction, then because 5 people walk here or 5 charges pass here, then when they recombine, I will have 10 charges passing by per second lah. Alright, another interesting thing for you that you may want to keep in the back of your mind, in general, the higher the resistance, the lower the current in the branch lah. You can think of it as they are coming here, if let's say this is a 10 ohm resistor, and let's say this is a 30 ohm resistor. Alright, then the current three more time charges will try to move through the 10 ohm resistor. Alright, because most people, it's easier for them to travel to the 10 ohm resistor, so I expect to have a lot of people going through here. Alright, only the very hardcore one will go through here lah, the 30 ohm resistor lah. So that's how it is lah. The higher the resistor, the lower the current that you will see in the branch here. Alright, for potential difference, however, the potential difference in the parallel branch is equal to all the components that are in the same parallel branch here. So in this case, the voltage at R1 must equal to the voltage at R2. Alright, so let's just look at an example here. Let's say I got a 2 volt battery here. Alright, and then I have an ammeter here and it measures 3 ampere or 3 no, sorry, not joules per coulomb, 3 coulomb passing by per second. Alright, which means over here also I have 3 amperes coming by over here, not 3 joules. So each of these coulomb of charge will have 2 volts of energy, or rather 2 joules per coulomb. Alright, since each charge over here, before it hits anything, still has 2 joules per coulomb of charge, and since it can only take one path, it cannot split itself into two and take both parts. So each coulomb of charge cannot split itself into two and decide to I want half of my body to go here, the other half to go here, and I will split 1 joule. Since they can physically only take one path, that means to this charge that's taking, let's say, the on top path here, this is the only resistance it encounters, because after that it ends here, right? And it must expended all its energy before going back into the battery. So that means the amount of energy expended here is also 2 volts. If I have a charge that decides to take the bottom path, again to him, he takes the bottom path. This is the only resistance it encounters throughout its journey before going back to the battery. Therefore, it must expend all the energy over here, 2 volts. So if we were then to look at the current in each of the branches, so I take over here, I equals to V over R. So the voltage is 2, the resistance is 2 ohms. Then I get that the current here is 1 ampere. So that means here is 1 ampere. So if I have to look over here, I do I equals to V over R again. The voltage again is 2 volts. The resistance is 1. Then I get 2 ampere. So you can see that basically whenever the resistance is lower, 1 ohm, the current that can pass through will be higher. Alright, it's like an inverse kind of relationship, but I wouldn't say it's inverse lah. Mathematically that's wrong lah. So basically the higher the charge in a proportional manner, that's how much it will increase or decrease by. So the higher it is, the lower the current. The lower the resistance, the higher the current. Alright, so this is a summary. In a parallel circuit, the currents is the sum of all the currents will equal to the current in the main branch. And for potential difference, the PD across each branch is equal to the potential difference across each of the individual branches or the whole circuit, if only the parallel branches are in the circuit itself. Alright, so let's talk about resistance then. Alright, I do not want to go into the derivation, but I can just introduce the formula to you. The formula is this. It sounds like a mouthful, It actually, in fact, it is a mouthful, The reciprocal of the effective resistance of resistors, 1 over R, is the sum of the reciprocal of all the individual resistances. Basically, it's this statement. If I want to effectively replace 1, 2, 3 resistors with just one equivalent resistor, then the equivalent resistor or the effective resistance is given by this formula. Now, I know this is the notes, this is the suggested formula from the textbook, but can I ask that instead you use this formula instead? Alright, it's the same lah. Except that the 1 over, I just shifted it over here and then it becomes negative 1 lah. Alright, why is it that I would prefer you to use this? Because they are equivalent. Why can't you just use this? Because the tendency is that we will make some common mistakes lah. So I just show you what are some of the common mistakes made by students lah. So if they use this formula, the effective resistance, so everything perfect 1 over R effective is equals to, let's say the resistors are 1 ohm, 2 ohm and 3 ohm resistors in parallel. So what they do is 1 over R1, 1 over 1, 1 over 2 plus 1 over 3, then they put 1 over 6. Then they say R effective is 1 over 6. Alright, so this is a common mistake made. Alright, a few things that you need to take note. 1 over 1 plus 1 over 2 plus 1 over 3 is not 1 over 6. The tendency is, I don't know why, whenever you're doing physics, your math brain switch off, you just take 1 plus 2 plus 3 equals 6. This is not how fractions work. The other thing that they make a mistake, after they calculate this, then they happily just say, oh yeah, this is the final answer. When actually they are supposed to get the reciprocal of this to get the R effective. So what do you do instead? I rather you use the formula here, the one that I suggested. Alright, so what you do, you just write it out, the effective resistance, then you just take 1 over 1 plus 1 over 2 plus 1 over 3, then you put inverse. Now I don't want you to do any fancy manipulation of fraction, just punch and this whole thing into the calculator and you get the final answer. I would rather you do this than do this and risk making a mistake. Alright, which brings me to my next point. It is a bit weird that when I add resistors, I got a 1 ohm resistor, 2 ohm resistor, 3 ohm resistor, I plus together, then it become only 0.545, which is less than any of the individual 1, 2, 3 ohm resistor. How is that possible? Alright, going back to our analogy of the tunnel that we learned in R equals to rho L over A, if there's only one resistor, then that means all the charges are trying to go through this resistor. Right, so therefore there's a lot of resistance, because remember each charge is made up of a lot of electrons, so they are all just trying to squeeze their way into this. So whenever I add more resistors in parallel, I actually give them more options for them to travel. Effectively, I'm increasing the area of the tunnel. So whenever I increase, therefore it becomes easier, because not all of them have to go here. Some can go here, some can go here. So therefore, when I add more resistors in parallel, it will actually decrease the resistance of the circuit. Alright. So let's go through a work example here. I'm tasked to find I1, I2, I3 and all the V's here. So I just want you to take note, this whole chapter basically only use one formula, which is V equals to IR. And I need you to take note that when you are using V equals to IR, you must be using the correct V, the correct I and the correct R across the same component. So let's look at this. I got a 6 volt battery. I have no other resistors in the circuit except for these two that are in parallel with one another. So which means if I am a charge and I decide to take the top path here, the path that I'm tracing here, that means I only have one resistor. That means I must expend all my energy at this resistor, 6 volts. The same here, if I got a charge that goes into the bottom branch, I need to expend all my energy here. So once you are done with that, then if I'm supposed to task to find I1, then you just take 6 divided by I equals to V over R. 6 divided by 10, I get 0.6 amperes. So I got 0.6 amperes of current here. V over R is again 6 over 20, I get 0.3 amperes here. 0.3 amperes here, which means that the current in the main branch here, alright, this is where the main branch make a lot of sense. It's the branch of the current of the circuit before it splits up into the more smaller branches, parallel branches. So the current in the main branch, or I3, is just the sum of these two. So 0.6 plus 0.3. So you get the answer like this. Alright, so in general, our housing circuits are all placed in parallel and not in series. Alright, a few reasons is because, one, they will glow more brightly because they have higher current and voltage per bulb. The second advantage is that even if one of them blows, the rest will still remain functioning. But actually, the main reason I would say is that because it allows the same voltage to be across each branch. So your housing in Singapore, at least, the voltage supplied by the power company is 240 volts. If I place in series, that means if I have a lot of lights, then this 240 volts will then split itself up. The more I place, the more it will split itself up. Alright, the effect is that it will decrease the voltage per bulb, but at the same time it makes it difficult for manufacturers to build, because they then have to build their bulb to ensure that there is a range of voltage that you can apply. So it's much easier that I design a bulb for 240 volts and all bulbs are allowed to work at 240 volts, and then I place them in parallel. Alright, so that's all. Alright, so just a quick example just to check if this is the EMF of the battery. Alright, in a series circuit, the voltages will be split. Alright, if they are the same bulb, then they will split equally. So the EMF will be divided by 2. Alright, whatever the value of the EMF will be divided by 2. While in a parallel circuit here, the EMF will be the same across each branch. So this fellow will have voltage of equivalent to the EMF. Alright, so the potential difference in the series circuit is already half of that in the parallel circuit. Alright, the resistance of each bulb doesn't change because it's just the resistance of the bulb. And therefore I can then calculate the current by taking I equals to V over R. You will see then also that the current in the parallel branch is greater than the current in the series circuit. So that's why we use this parallel in home circuits. Alright, just a quick summary. If I have a a parallel circuit connected to a battery of EMF, of a certain EMF, then this current that coming out of the battery is the main branch current, or sometimes we call it the total current. Alright, each individual parallel branch has its own current, I1, I2, I3. So the current in the parallel circuit, you must remember, is the sum of all the individual currents in each branch. So I1 plus I2 plus I3 plus I4, don't know how many you have, must equals to the total current or the main branch current. While the potential difference across each of them, because remember the charge when it moves will only take one path, it will be equivalent to the EMF of the battery. So that's why it's here. Same. V1, V2, V3 is the same. And finally, to calculate the effective resistance, strongly recommend that you use this formula instead of the one suggested in the notes. Alright, so we move on to the last part for the combined signs. What happens if I have resistors both in series and parallel? How do I deal with it? How do I calculate it? Alright, so this is just a recall. In a series circuit, the sum of all the individual resistors, the resistance of the resistors will give you the total resistance of the circuit. But in parallel, you are supposed to use this formula, so remember. So when I have a combination circuit like such, then your job is to find the effective resistance of the circuit, 1 over 3, 6 and 4. So this is actually a parallel branch that is in series with this fella. Right, I need to resolve this first, then after that I can add to this in series to calculate the total resistance. You may ask, why can't I just take 6 plus 4? Because this is not actually in series with this. This 4 ohm is actually in series with both of them. So I need to find the effective resistance of this. So how does one do the calculation? The effective resistance, I resolve the parallel part here first, is 1 over 3 plus 1 over 6 inverse. Then I add on the plus 4 which is in series with it. Alright, 1 over 3 plus 1 over 6 is 1 over 2 inverse plus 4. So it's 2 plus 4. So the final answer is 6 ohms. So effectively these three resistors, I combine them, act like a 6 ohm resistor. Alright, what happens if my circuit or my resistors are arranged as such instead? This is actually a series in a parallel branch lah. Alright, so the total effective resistance of this is just, I need to resolve this series first, get an equivalent, then I can then combine with the parallel branch here. So it's 1 over 3 plus 4 plus 1 over 6 inverse. I plus these two together, I get this one. Then it's in parallel with this one, so therefore 1 over 7 plus 1 over 6. 1 over 7 plus 1 over 6 inverse, and the final answer is 3.2 ohms. Alright, the only important part that you do need to take note of is that you should use the correct V, the correct I, and the correct R when you're doing the calculation for V equals to IR. Alright, so an important skill set that you must have when dealing with a combination parallel series circuit is this: how does one redraw a circuit? if I look at this looks also complicated. Alright, the redrawing of the circuit will help you actually see the parallel and series branches clearer and help you to solve the questions properly. So the step 1 is actually, what I like to do is to trace the direction of the conventional current from the positive terminal. So what I do is I draw the battery first, positive, negative. So I trace positive, negative, what it meets first, it meets a junction. So all junctions you must also draw. So I draw one junction, I meet a junction A here. Alright, at the junction A, it splits up. In one of the branches, I have 3 1 ohm resistor. 3 1 ohm resistor. Then after that, after the last 3 1 ohm resistor, I meet another branch. So I draw. I literally just draw. This is B. In one of that branches, I follow. I have 6 1 ohm resistors all in series with one another. 1 1 1 1 1 and 1. Alright, then this one actually will combine, they meet at the junction. So I have a C here. Then actually this junction is between B and C. I have a 3 ohm resistor here. Alright, after C, then I encounter 3 1 ohm resistors again. I'm going to run out of space. 3 1 ohm resistors again. After which I combine at D, and between A and D I have another resistor here. I mean at D, between A and D I have another resistor here that is equivalent to 2 ohms. Then after that, from D it goes into the negative part of the battery. So with that, it becomes more manageable for you. Alright, you know that you need to plus all these, plus all these, plus all these. Alright, so this one is equivalent to being a 3 ohm resistor because they are in series. This one is equivalent to being a 6 ohm resistor, and then this one is equivalent to being a 3 ohm resistor. So how to calculate? You take 1 over 6 plus 1 over 3, you inverse, you get this fella. Then they are in series with these two, so whatever this number is, you plus 2 plus 2, they get us a number. Then that number is 1 over that number plus 1 over 2 inverse, you get the effective resistance of the circuit. Right, so let's just see how to solve one question here for resistors in series and parallel. Remember, use V equals to IR. When you want to use V equals to IR, your V, your I and R must be across the same component. Alright, so let's look at the question. I'm tasked with finding the current I1 over here, which is the current in the main branch. Alright, I already have current in the bottom branch. From my parallel circuit, I know that if I find this, I should be able to plus this, and I get the current in the main branch. So that's what my intention is. Alright, but before that, I kind of do need to know what is the voltages here. Since they are parallel here, any charge that pass by here and take the top path, it will expend all its energy across these two resistors. So therefore, over here is 3 volts, and over here is also 3 volts. Alright, so from the top branch, I can then also find, I'm going to label it I2. So I label I2 is equals to V over R. The voltage is across both resistors. So I must use, if I use 3 volts, then I cannot just use 2 ohms or 3 ohms because it's the total of between here and here. So I must use 3 over 5. So then the answer is 0.6 amperes. Alright, so once I have this 0.6 amperes here, let me readjust. Then all I need to do to find I1 is just 0.6 plus 0.2. The answer is 0.8 amperes. They asked me to find the potential difference between X and Y. So this one is slightly a little bit more complicated. So if this is a 3 volt battery, you remember that any current coming by here will still have 3 joules because it's all per each coulomb, because it hasn't passed by anywhere where it can expend its energy. Alright, so over here it still has 3 volts. It still has 3 volts here. Alright, so they ask you to find the potential difference between X and Y. So basically they're asking you to connect a voltmeter here and tell me what's the potential difference. Your job is to tell me what's the potential here and the potential here. I take the two numbers, I minus, I should get the potential difference. So if if the current here, sorry, it's not 3 volts here. If the current here, as I calculated just now earlier, was 0.6 amperes, I can then calculate how much voltage is spent across the 2 ohm resistor. Because they are in series, right, just this top branch, so the 0.6 travels throughout both of the whole resistor. So if I use this and find the V equals to IR, I can actually get that this value is 0.6 times 1.2, 2, the answer is 1.2 volts. That means I expended 1.2 volts of energy here, which means if I had 3 volts here at the start, and I expended 1.2 volts here, I will end up with 1.8 volts here. If I do the same calculation over here, I use V equals to IR, 0.2 times 1, the answer is 0.2 volts. I know that if I started off with 3 volts over here, and I expended 0.2 volts here, I will end up with 2.8 volts here. So now I know the potential at each of them. The potential difference is then just 2.8 volts minus 1.8 volts. The answer is 1 volt. Alright, and then they asked me to calculate the resistance here. Because I know already that this is 2.8 volts, which means here is also 2.8 volts. How much energy expended here? And I know the current running through this whole bottom path is 0.2 amperes. I can then use R equals to V over I. And the voltage is 2.8, current is 0.2, and I get that the resistance is 14 ohms here. Alright, a little bit complicated, but you must be systematic in your understanding of this. Right, so this is the solution to the question just now. Alright, we move on to the final 2 portions, which is only relevant to the pure physics students. The combined science students, you are done with the chapter already. So for potential divider circuits, what it means, I know later on that you will find the formula and it will look quite complicated looking, but actually remember that the basic of it is quite simple. So I'll just illustrate with an example. So if I have a circuit with a 3 volt battery in series with 2 resistors, one ohm, one 2 ohm, how much voltage each is across each of the resistor? Alright, most of you will be easily able to tell me that it's actually 1 volt and 2 volt here now, because this resistor is lower resistance than this, so the charge will spend less energy here compared to this lah. Right, and because you originally started with 3 volts, that's how we split in this way lah. So how do you actually come to this number of 1 volt and this number of 2 volts? So actually you did a little bit of some mathematical jumps here and there lah. So what you did was actually you took 3 volts here, the total voltage, alright, and this 1 ohm resistor will take 1/3 of the whole resistor, because the whole resistance is 1/3. So usually what people do is they did this and they will get 1 volt. Alright, so in other words, to just make it of the form that you will encounter a lot more, it's just 1 plus 1 plus 2. That's how you got this, right? 3. So if I were to then replace them with symbols, then V at the 1 ohm resistor is actually the EMF of the battery multiplied by R1 over R1 plus R2. That's how we got the formula here. Alright, and the 2 volt is actually just EMF times R2 over R1 plus R2. That's how you get this. Alright, so essentially this is a potential divider circuit. So what a potential divider circuit is, it is a circuit with at least 2 or more resistors arranged in series, and because of them being in series, they divide the main voltage here into 2 different parts here across each resistor. If there's 3, then you divide into 3 lah. Alright, so the formula that we derived there, it looks complicated, but I needed you to remember that it wasn't, right? It was something that you could easily understood or derive naturally. Right? The other important thing that you need to take note of, the larger the resistance is, the more the voltage that it will take. That means if this is bigger than this, it will take a bigger chunk of the potential difference in a proportional manner. So let's look at how to solve a question like this. So you got a 6 volt supply connected to a 10 ohm and a 20 ohm resistor. You place the output voltage here, so they ask you to measure the output voltage here. So all you need to do is to take the total multiplied by this one 20 over the total resistance, which is 20 plus 10. So 6 times 20 over 30. The answer is 4 volts. 4 volts. Yeah. So that is a potential divider circuit. Alright. So some other things that you can do in a potential divider circuit is that you use a variable resistor and one fixed resistor. So because now you have the ability to control the resistance here, I can vary then also the voltage over here. When I vary the voltage over here, it means I can also vary the voltage here. Alright, so let's just think about what happens when I increase R1. So when I increase the resistance of R1 here, the voltage 1 across the resistor R1 here also increases, because the higher the resistance, the higher the voltage it takes. Alright, because this plus this must equals to the V here. When this one increases, this one must decrease. V2 increase and V2 is actually at V out, so V out decreases. So this kind of reasoning and explanation is how you should answer a question whenever you are faced with an explained question in the potential divider circuit. Alright, so let's look at how to solve a question. There are maximum and minimum output voltages. 9 volt, 2 resistor, one is a variable, one is a fixed resistor. They asked me to calculate the maximum and the minimum output voltage. So output voltage is here, V out. If I want a maximum V out, that means I need here to be as least as possible, because the smaller it is, the lower the voltage over here. So the least that it can go this variable resistor is from 0 to 100. So I do 0 degrees, 0 ohms here, sorry, not degrees. So V out therefore is then the total voltage 9, which is over here. It is 50 over 50 plus 0, because it's 0 ohms here. So 9 times 50 over 50, the answer is 9 times 1, so the answer is 9 volts, which makes sense, because if there's no resistance here, it's as if this resistor is just a normal wire lah, 0 volts, 0 ohms. So to get a minimum V out, I need to take 9 times. The only way I can get minimum is when this fella here is the max lah. So it's at 100 ohms now. So it's 50 over 50 plus 100, which is 9 times 50 over 150, and that will give me 3 volts. Right? So this is how you solve questions involving potential divider circuits. Now, other than just using a variable resistor as one of the two resistors, you can also use something called a potentiometer. A potentiometer is basically you have one big resistor here, but your output voltage here you put in parallel to one of the portions, and over here this connection point here is movable. We call this a slider contact lah. So you can move here and you can move here. So for me to get V max at V out to be the highest it can possibly go, that means it needs to be across the whole resistor. So it's at VB. So at VB it will be max. For me to get V out to be the smallest, that means I need it to be as close as possible here. Alright, if I can put it here where it's across nothing, parallel to nothing here, a wire, then it will be at 0 volts lah. Alright, so let's just do a simple question. I got a 6 volt battery connected to a potentiometer of 100 ohms. They asked me to calculate the V out when it is at A, B, or the midpoint of AB. So for VA, it's very easy because it's parallel with nothing. So it's actually 6 times parallel the resistance here is actually 0. So 0 over a total of 100. So the answer is 6 volts. Alright, so for 0, what am I talking about? Sorry, 6 times 0 over 100 is 0 volts. Alright, so VB, if I put it all the way here, now it's the total of 6 volts times 100 over the total resistance of 100. So the answer is 6 volts. If it's at the midpoint, then it's 6 times. Midpoint means I use halfway here, so this should be 50 ohms. 50 over 100 ohms. It gives you 3 volts. Alright, so that is essentially a potential divider circuit. It is simple enough concept to understand. Alright, which brings me to my last point, the input transducers. Alright, so the last portion of this chapter is input transducer, and we use input transducers in a potential divider circuit to help us automate certain electrical processes lah. Alright, so I'll explain in a little bit more detail. Alright, what are transducers? Transducers are things that convert electrical energy into other forms of energy, or it converts other energy into electrical energy. Alright, either anything that deals with electrical energy as one of them is a transducer. Now, when it converts other forms of energy into electrical energy, we call them input transducers. When they convert electrical energy to other forms of energy, we call them output transducers. Alright, so these are what transducers are. Input converts non-electrical energy to electrical energy. Some examples are microphones, thermistors, thermocouple, and LDR. So you speak into a mic, so it's actually just sound energy. The sound energy is then converted to electrical energy lah. Alright, and then it's stored as a signal. Now, these two here are bolded because we are going to use them in the study of transducers in potential divider circuits. Output transducers are a little bit easier for you to memorize. Electrical energy to other forms. Basically, a lot of things are output transducers lah. Loudspeaker, LEDs, voltmeter, ammeter. Basically, they convert electrical energy to KE. Your fan is also considered a form of output transducer. Your light, your speaker, everything is an output transducer lah. As long as it uses electricity and it does something with the electricity, it's an output transducer. Alright, so looking at the two input transducers here that we have to memorize and study. Alright, one of them is called the thermistor. Alright, so a thermistor is drawn like a fixed resistor first. Alright, you draw somewhat like a variable resistor, but instead of having an arrowhead, you just draw another line like that. So you must remember this thermistor. Alright, what's unique about thermistor? It is a resistor where the resistance varies with the temperature. Alright, how does it vary? The higher the temperature, the lower the resistance. Or the lower the temperature, the higher the resistance. Now, this is something you must know and memorize. Alright, so how I usually memorize is that the resistance is actually varies oppositely with the temperature. So higher temperature, lower temperature, higher resistance. Alright, so I'm just going to jump a bit ahead to the LDR portion. I'll introduce to you the other input transducers that we are going to discuss. So an LDR here is a light dependent resistor. It is one where the resistor actually varies with the intensity of light falling on it. How to draw? You draw like a normal resistor, draw a circle around it, draw two light rays dropping on it. Alright, so this is an LDR. Alright, so for LDRs, the relationship of resistance and the amount of light, the higher the light intensity or the more the light that is falling on it, the lower the resistance. Or the lower the light intensity, the higher the resistance. Again, it's similar to thermistor, it is opposite. So how I remember, I always tell the students memorize that the relationship for the resistance is always opposite to whatever is happening to it lah. For light dependent resistor, if it's increasing, then it will drop. Alright, the same with the thermistor. The higher the temperature, the lower the resistance. Alright, so how does having an LDR or thermistor within a potential divider circuit, how does it work and what does it do? Alright, so let's just look at the circuit here. So this is a typical potential divider circuit. One is a fixed resistor, one is a thermistor. So let me discuss what happens when the temperature decreases. When the temperature decreases, the resistance of the thermistor increases, which means the voltage of the thermistor increases. The voltage across here increases, which means because this increase, this fella here must decrease. Alright, so what's the point of having it like this? So it acts as a temperature sensor in a sense. So what kind of application do you think you can put it? If I were to put an aircon across here, then actually what happens is that when the temperature drops, V out drops. If all electrical equipments, they have a certain voltage called a threshold voltage. Anything below, nothing happens, but once you hit it, then actually it will switch off lah. So when the temperature drops enough, the voltage here will also drop enough, and then my aircon will automatically switch off lah. So if it gets too cold, that means my aircon switch off. Alright, so it's an automated temperature system. Alright, so what if I want to automate, let's say, the use of a heater, that I want it to to switch on when the temperature drops, especially in countries with winter, the temperature drops a lot. I want it to switch on. Then in that case, I would then put my heater here. Alright, because the lower the temperature, the higher the thermistor resistance, the higher the voltage across the thermistor. Since the heater is parallel to the thermistor, then once the voltage increase beyond a certain limit, then the heater will switch on. Alright, so these 5 points here, or 1, 2, 3, 4 here that you see, is what you should say to explain whenever you encounter a explain question with input transducers in a potential divider circuit. Alright, apart from explain questions, there's also a typical standard calculation questions. So let's look at the calculation question and how to deal with it. I got a 6 volt thermistor and a 100 ohm resistor. They tell me at 0 degrees my thermistor is at 500 ohms, at 100 degrees is at 50 ohms. So they asked me to calculate the voltage reading here when it's at 0 and 100. So at 0, my thermistor is at 500 ohms. Alright, so how to calculate? 6 times 100, because remember the voltmeter is across this resistor which is 100, over a total of 100 plus 500. Alright, so for V 100 degrees Celsius, alright, at 100 degrees Celsius, the voltage, the resistance of the thermistor is at 50 ohms now. Alright, so because it is at 50 ohms, then all I need to do to calculate is actually 100 over 100 plus 50. Alright, so that will give me 1 volt here, and that will give me 4 volts here. Right? So simple enough. Alright, so let's have a look at the solutions here. Alright, so basically that's how you deal with calculation questions of the manner. Alright, so just check the solutions. At 0 degrees, it is 100 over 100 plus 50, this 1 volt. Alright, so just take note of this. So LDRs also work the same way. Alright, so let's look at how to solve questions involving LDR now. Again, if my LDR is part of the potential divider circuit, so when my light intensity over here decreases, it means my RLDR will increase, my VLDR will increase, and therefore my Vout will drop. Alright, so certain things you can do to automate lah. A few things you will take note is that light intensity decrease, my Vout decrease here. If I put a light here, then actually when it becomes dark, then actually my light will switch off lah. So this kind of situation is when you can find certain systems in countries where, in places where they are trying to simulate the outside environment for let's say an enclosure for animals, right? So they automate the system so we don't have to have a guy go around and switch off the light. Alright, so basically what happens is that when the light intensity decreases, the Vout here decreases. So when it becomes dark, the lamp will switch off lah. So for like the animal enclosure, then it will automate the system lah to simulate night, the night conditions lah. Alright, the one that you find in the lamppost in Singapore where they automate the system for you is where they put the light bulb over here lah actually. Alright, again the same, when my light intensity decreases, my RLDR decreases, my VLDR increases, therefore it will then switch on. Alright, so that means when it becomes dark, the voltage is now high enough to switch on the light lah. So you don't have to have somebody. We have these systems in the lampposts across all our roads and expressway lah. When it becomes too dark, the light will switch on by itself lah. Again, explain type questions, you are supposed to answer in this manner. Say this, and then this. Alright, let's do a bit of a calculation first. Apologies. So for LDR calculation, let's try. So when it's dark, the resistance of the LDR is 100. Okay, I drew the circuit here because it's all words lah. Then if it's wordy, then it helps to actually draw something so that it can help you visualize. When it's dark, the LDR is 100 ohms, and when it's bright, it's 5 ohms lah. Alright, so when it's dark, it's 100. So the output voltage is over here. Sorry, it's 100 kilo ohms. Alright, so when it is dark, I take 9 times the V out is across the 10, so it's 10 here over 10 plus 100 lah, because when it's dark it's 100 kilo ohms lah. Alright, then you do the calculation, you get 0.818 volts. Alright, when it's bright, the resistance of this one is 5. The V out is across still a fixed resistor of 10 kilo ohms, so it's 10 plus 5, the total resistance, and that will give you a total of 6 volts. Alright, so I'm just posting the solutions here. That brings us to the end of the chapter for DC circuits. If you do have questions, please just drop me and ask via the usual means lah. Alright, thank you, bye bye.